All right, hello from Florida again. We're going to pick up with a new chapter. Remember, this is not going to be on your test on Friday, but this is sort of a continuation of a discussion of aromatic compounds, and particularly benzene. But chapter 18 deals with reactions of benzene. And what we'll find is that aromaticity that stabilizes benzene is going to be the driving force for a lot of these reactions that we will see. So most of the reactions of benzene follow a mechanism that's known as electrophilic aromatic substitution. And so what that means, as the name implies, is that we're going to be using an electrophile to react with benzene, and the end result is going to be taking a hydrogen at one of the positions on a benzene ring and replacing it with some electrophile. So these are the classical reactions of benzene, from which a lot of other chemistry has come. So really all we're going to do, like the scheme here says, is react benzene with some highly reactive electrophile, and that's going to replace one hydrogen on the benzene ring with that electrophile. And if we wanted to imagine how that might happen, it sort of mirrors double bond chemistry in that one of these pi bonds will reach out from benzene and grab that electrophile. That will get us to a highly reactive cationic intermediate where we've added the electrophile and generated a carbocation on the other carbon from the double bond, and we will get rid of that proton at the position where we've added the electrophile to go to the substituted benzene ring. And so it's really important to recognize that loss of the proton restores the aromaticity of benzene. And that's sort of really what provides all of the driving force for these reactions to happen. So we'll work through a series of reactions, but I want you to focus in on this generalized mechanism because all of them are going to proceed through this exact same scenario. The only difference is going to be exactly what we do to generate this reactive electrophile. So the first reaction that we're going to talk about deals with the halogenation of benzene. And so what this reaction involves really is the installation of a bromine or a chlorine onto the benzene ring. It only works for bromine and chlorine. And in the context of bromine, here's what it looks like. So in both of these cases, what we will do is treat benzene with the molecular halogen, so Br2 or Cl2, and then we will use an iron Lewis acid that contains the same halogen. So for Br2, we'll use FeBr3. For Cl2, we'll use FeCl3, but same idea in terms of how this reaction happens. What we end up doing, again, is replacing one hydrogen on that benzene with a bromine atom. And so really the mechanism here is going to involve generating a highly reactive Br plus equivalent that can add to benzene. And so the way in which this works, if we think about molecular bromine, those bromine atoms have lone pair electrons on them, but because bromine's so electronegative, it's a pretty good electrophile. It's not electrophilic enough, however, to overcome the aromatic stability of benzene. So in this case, we need this Lewis acid to accept electrons from bromine. And what that's going to do is really activate one of these bromines towards substitution so we've added electrons into iron, becomes negative because it was neutral. That central bromine is sharing electrons with iron, so it becomes formally positive. But what happens when that bromine is positive, it starts to suck electron density from this bromine on the end, which develops a very strong partial positive charge. And it's actually this bromine on the end that's going to interact with benzene to do this electrophilic substitution. And so here's the part that looks similar to the generic reaction we drew. That double bond of benzene reaches out and grabs that bromine. We spit out a bromide system. We spit out that Lewis acid and the bromine. And the key intermediate that we get to after that is again going to be this cationic species where, let me draw the double bonds exactly the same way. So what we'll get out of that reaction is this cationic species where we've added the bromine, still have the hydrogen that was in that place, and on the other carbon where we took electrons away, we've got this carbocation. And so we also get this FeBr4 Lewis acid that just goes away at the end of the day. But it's this carbocation species that's important. We'll get back to benzene by losing a proton from that species to regenerate the double bond and regenerate the aromatic core of the system. And so then at the end of the day, what we've found is we've just replaced one hydrogen from benzene with a bromine. Would be the exact same mechanism with the chlorine material. You just end up replacing that hydrogen on benzene with a chlorine. So again, all of the gymnastics that are happening with whatever goes on the line in these reactions, they're just coming together to make a hot electrophile that can react with benzene so that it breaks the aromatic ring and then reforms the aromatic ring. So this reaction in the context of chlorine would add in Cl2, FeCl3, and so again in that case what we would do is replace one hydrogen on benzene with a chlorine. So the second reaction in this electrophilic aromatic substitution chemistry is the nitration of benzene. And so what this transformation looks like is this. We will take a benzene ring, we cook it up with sulfuric acid and nitric acid. So HNO3, H2SO4. That mixture will provide us an NO2 electrophile so that the nitration event is going to give us the installation of that NO2 group, and then that is the functional group that's known as a nitro group. Okay? And so what we'll see as far as this second reaction goes is that mixture of sulfuric acid and nitric acid, that's going to come together to give me NO2 plus. And so when I form that NO2 plus, that's what's going to react with benzene through that same mechanism that we've seen before. So if I think about what the Lewis acid for nitric acid, the Lewis structure, what am I talking about? The Lewis structure for nitric acid would look like this. And when that material gets mixed with sulfuric acid, even though sulfuric acid is, both of these things are nominally acid, sulfuric acid is more acidic than nitric acid, so you can actually do an acid-base reaction where sulfuric acid will actually protonate nitric acid. And so we'll get a material that looks like this, where we've made an OH2 plus species. That's going to be obviously a nice leaving group, can spit out neutral water, and that's going to give me this NO2 cation that is going to react with benzene. So it's actually this material, this NO2 group, which is going to serve as the electrophile that will react with benzene. So then the double bond of benzene will reach out and grab that nitro group. And so this is the part that should look familiar and similar to the other two reactions we've just seen. I'm going to add on the NO2 group, still have that hydrogen that's in place, and the neighboring carbon will be positive. And we will lose that hydrogen to get rid of that positive charge and restore aromaticity so that the total outcome of this reaction is installation of that NO2 group onto the benzene ring. So hopefully you sort of see the similarities that we have with these few reactions. So Again, with the nitration of benzene, that mixture of nitric acid and sulfuric acid, they come together to generate NO2. Again, this is going to be the E+ reagent that's going to be reactive. That will come together under those same two addition-elimination steps that we saw in generic terms with the substitution of benzene. Okay? The third transformation that follows this paradigm is what's called sulfation reaction. And so what that material does is it takes benzene. It uses a reagent known as fuming sulfuric acid. So what is that? That is basically sulfuric acid that has had sulfur trioxide dissolved in it. So you have SO3 floating around in this sea of sulfuric acid. Okay? And when that mixture is reacted with benzene, again, we're going to replace one hydrogen on benzene with this SO3H group. And so this is the way to make what are a functional group known as benzene sulfonic acid. Okay, so again, what we're going to have in this case is the formation of a highly reactive species. So this mixture of sulfuric acid and SO3 is going to essentially give you this SO3 plus electrophile. So this mixture leads to this SO3H plus cation. That's going to be our electrophile, and then everything else is the same. Double bond reaches out and grabs that sulfur. So now we've used one of those double bonds to add the SO3H group. Still have that hydrogen in that position, but we've generated a carbocation next to it. So we again eliminate that hydrogen to go right back to the aromatic benzene ring. So all of these things sort of are hopefully looking very similar. So that's the third transformation, which is the sulfation of benzene. Okay, so what we've seen so far is addition of NO2 group, addition of SO3H, sulfonic acid, and the addition of a halogen. Turns out there are two routes that we can use to add carbons to a benzene ring. Those are named after two dead guys, so Friedel and Crafts. So these are called the Friedel-Crafts reaction. We can do an alkylation, and we'll see later that we can do an acylation. So here's what the alkylation looks like. In this case, we will take benzene, and the reagents that go on the line are typically an alkyl chloride of any carbon piece that you can think of. And then we add a very strong Lewis acid aluminum trichloride to that. And the net result is going to be installing whatever that R group is, the carbon piece, to the benzene ring. And so the thing to keep in mind, again, is that this mixture of a carbon chlorine and aluminum trichloride, it's going to give us as the key electrophile a carbocation, which is going to be highly reactive with benzene. So in the context of methyl chloride, if I were to take this and say methyl chloride plus aluminum trichloride, I would expect that mixture to give me methyl carbocation, and that's actually what's going to replace one of the hydrogens on benzene. So how does this reaction work? It's very similar actually to the activation of bromine, etc. So if I have a carbon species with a chlorine on it, and I put in a really strong Lewis acid like aluminum trichloride, that chlorine can use its lone pair electrons to dump into the aluminum empty p orbital, and so that'll give me this complex where aluminum has become negative, chlorine has become positive because it's taken an extra bond, and that material will then collapse by breaking the carbon-chlorine bond and generating in the flask carbocation plus AlCl4, which again is byproduct of this reaction that we don't care about. But it is this carbocation species that is what is necessary to react with benzene through the electrophilic aromatic substitution reaction, so that we will add that carbon group, still maintain that hydrogen attached to the same carbon, and generate the carbocation next to it. So hopefully you're seeing a theme here, right? It's the same thing over and over again. Get to this cationic intermediate, and then the elimination of that proton at the site where the substitution occurs will regenerate the aromatic ring and leave behind that substitution piece where we've added a carbon. Now, in a case like this where our key intermediate in this case is a carbocation, we have to keep in mind that carbocations can rearrange. So we have to keep in mind that depending on the alkyl halide that we have, we can see rearrangements occur in this case. So if we look at a few examples, we can illustrate that pretty easily. So in a case like places where the carbocations are pretty stable and don't have any desire to rearrange, we can predict the outcome of the reaction pretty easily. So if I take, for instance, T-butyl chloride and aluminum trichloride, I would expect for this reaction to spit out T-butyl benzene. Similarly, if I have even a primary or methyl group that doesn't have the opportunity to rearrange, so if I think about ethyl chloride and aluminum trichloride, I expect this single transformation to happen, and I'll add on that ethyl group at the benzene position. But these are tractable because we don't have the opportunity for a rearrangement. If I think about this third example, what if I have propyl chloride and aluminum trichloride? In that case, my outcome is going to be not the addition of a propyl group, but the addition of an isopropyl group, where I've got a branch point at the site where benzene reacts. And again, of course, this is because that combination of aluminum trichloride and propyl chloride will originally give me a primary carbocation, which can undergo rapid rearrangement to a more stable secondary carbocation, followed by reaction with benzene. Okay, so you do have to look out with these Friedel-Crafts alkylations for the potential for a rearranged product. But other than that, this reaction should be quite straightforward. All right, so that's, we've seen now how to add, if we scroll back up here, we've seen how to add bromine to a benzene ring, or chlorine to a benzene ring. We've seen how to add a nitro group with sulfuric acid and nitric acid. If we use fuming sulfuric acid, we can add a sulfonic acid functional group onto the benzene. And here we just finished talking about adding a carbon group, an alkyl chain, to the benzene ring through the Friedel-Crafts alkylation. There is a sister reaction to the Friedel-Crafts alkylation, which is known as the Friedel-Crafts acylation. And so what that does is actually install an acyl group instead of an alkyl group. Functionally, it looks exactly the same. I'll take benzene. Instead of using an alkyl chloride, I'll use what's called an acyl chloride. We'll see some reactions of acyl chlorides later in the course too, but basically I have a carbonyl instead of an alkyl group. If I mix that material with aluminum trichloride, I would then expect to add the acyl group at that position. So again, ripping off the chlorine to make a carbocation, that's going to react with the benzene ring using the same exact set of conditions that we've already seen. So what ends up happening here is that mixture of aluminum trichloride and the acyl chloride is going to break that carbon-chlorine bond and will generate what's known as an acylium ion. So this is what's called an acylium ion. Okay, and the nice thing about acylium ions is that they're resonance stabilized. So I can actually dump in electrons from the carbonyl oxygen to stabilize that carbon by sharing that positive charge onto oxygen. And so this is important, an important distinction between the acylium ion and the carbocations that we saw in the last cases, is that acylium ions don't rearrange because they're resonance stabilized. Okay, and so no matter what the nature of R is on these systems, we will not see rearranged products in this case. And so if we think about a reaction under this framework, I can make a variety of different compounds just by changing the structure of that acyl group. So I could make methylphenyl ketone by using acetyl chloride, but in this case I can actually go ahead and make linear systems too if I use longer acid chlorides or acyl chlorides. So we can make a variety of different compounds under these conditions. So I'll just do one more example to drive the point home, but really the carbon species can be anything. So I could have this cyclic acid chloride with aluminum trichloride, and then I would just expect, again, to rip off that chlorine, make the acylium ion, tack that piece and whatever else is attached to it onto the benzene ring. So that is the Friedel-Crafts acylation. So those are the 5 transformations that use this electrophilic aromatic substitution step that we talked about at the very beginning. So all of these reactions have this generalized mechanism again, where the benzene ring attacks the electrophile, we add the electrophile, generate a carbocation at the neighboring carbon, and then eliminate the hydrogen at the site where the substitution happens, such that we re-establish the aromatic core of benzene and leave behind that electrophile. Okay, so that's that class of reactions. I have a few more reactions I want to add to the list of important changes to substituted benzene rings, but what these are going to do is use the products of these initial 5 reactions to do further chemistry. Okay, so there are a few others that we need to talk about. So the first one in this case is going to be the reduction of the nitro group. So we saw in the reactions of unsubstituted benzene that we have a way in which we can install this NO2 group. And it turns out what we can do at that point is we can convert that material to an NH2 by adding hydrogen and palladium on carbon, similar to how we would reduce a carbon-carbon double bond. Now, because benzene is so stable because of its aromaticity, those double bonds in benzene are not susceptible to reduction unless you really activate the system. So in this case, we'll leave behind those double bonds and just reduce the nitro group to an NH2 group. That gives us a compound known as aniline. Okay, so aniline can be produced by taking that nitro group, adding hydrogen, palladium on carbon to remove that nitro group and replace it with the NH2. Turns out you can do this reaction also with a metal reductant, so you can actually use zinc metal dissolved in hydrochloric acid. That will also give you the same outcome here. Now, the mechanisms for how this happened are not straightforward, so we're not going to spend an awful lot of time thinking about them. It's just suffice it to say that this is one of the, I think, fewer reactions in the class that you're just going to have to commit to memory. But hopefully you see an analogy with adding hydrogens across the nitrogen-oxygen double bond, similar to reducing carbon-carbon double bonds. All right, the next set of reactions that we need to look at are what is known as permanganate oxidations. And this is of benzylic hydrogens, so benzylic CH bonds. Okay? So again, another reaction we're not going to worry too much about mechanism, but what we can do in this case is this is a convenient route to making benzoic acid. So if I have made a compound that has benzylic CHs like toluene, I can actually take those benzylic CHs and oxidize them with this compound KMnO4, so potassium permanganate. The outcome of this reaction is going to be converting that species to benzoic acid. And so no matter what the carbon group is, so long as it has benzylic hydrogens, we will oxidize that site to a carboxylic acid. So I could have a more substituted alkyl chain, like this propyl group, and if I treat that with KMnO4, it'll chew that up to benzoic acid, so we'll get the same product. Okay? But again, notice that this is an oxidation of benzylic CH bonds. So if I don't have a CH in the benzylic position, whatever that group is will stay behind. So say I could make this di-substituted benzene ring where I have a methyl group and a T-butyl group. If I react that with KMnO4, even if I use a whole lot of KMnO4, I can oxidize that methyl group because it has benzylic CH bonds. So that position will get converted to the carboxylic acid, but I'll leave behind that T-butyl group because I have no CH bonds at that benzylic carbon with which to do the reduction. Okay. The third sort of one-off reaction modification of substituted benzene rings is what's known as the Clemmensen reduction. Okay, another one that we're not going to worry about mechanism at all, but this is what the reaction can do. I can take the products of a Friedel-Crafts acylation, where I have that carbonyl group directly attached. And if I treat that with the Clemmensen conditions, which is a mixture, it's an alloy basically of zinc and mercury. If I use this reaction with that carbonyl species, what I really get out of the end of the day is effectively the erasure of the carbonyl. So I'll just basically convert that C double bond O into an alkane CH2. So this is effectively a way to get rid of a carbonyl. So one thing to think about here is that this actually solves the rearrangement problem with the Friedel-Crafts alkylation, right? So if I want to think about this, if I remember when we talked about the Friedel-Crafts alkylation, that part of the problem here is that if I take that benzene ring and I treat it with an alkyl chloride that can rearrange, it will do it. right? So if I rip off that that chlorine to make a carbocation that's primary, it will quickly rearrange to a secondary carbocation, and even though I started with a linear alkyl halide, I'll actually wind up with this product where I've got a branched, rearranged product. Well, if I really, for some application, wanted that linear species, right, the Friedel-Crafts alkylation isn't going to work. So it actually turns out that I can solve this problem in a different way if I, instead of using the alkylation chemistry, let's add the same number of carbons but use the Friedel-Crafts acylation. So in that case, now the Friedel-Crafts acylation will proceed without rearrangement because the acylium ion, hopefully you will recall, is not something that rearranges. So I can keep that linear site, and then I can use the Clemmensen reduction to erase that carbonyl. So this is kind of a nice way to overcome that limitation of the rearrangement of the system with the Friedel-Crafts alkylation. All right, so those are three reactions that are sort of one-offs that you kind of have to memorize. So take the nitro and convert it to an NH2. We have two ways to do that. Take benzylic CH bonds and oxidize them to benzoic acid. And the Clemmensen reduction, which is a way to take a carbonyl and turn it into a CH2. Okay, the last bit of chemistry we're going to talk about for this first part of this chapter is something that's actually in a different part of your book. We're going to talk about a really important class of chemistry called diazonium chemistry. Okay, and you'll find this in your book in chapter 2210 to 2211. So that'll be something you want to look into a little bit later. So here's what diazonium chemistry is. And to do this, we had to learn how to make aniline first, right? So we need an aniline to do this chemistry. And remember, we've just figured out how to fix that problem from benzene, right? So if I start with benzene, I can do the nitration, and then I can convert that nitro group with hydrogen and palladium on carbon to the aniline, okay? But once I get the aniline, I can convert that material to a diazonium group. So here I'll treat with NaNO2 and hydrochloric acid, okay? And what I get from that mixture, NaNO2, sodium nitrite, and hydrochloric acid, is I'll convert that NH2 into a diazonium group. What a diazonium group is this. It's a nitrogen triply bound to another nitrogen, which is attached to that bond, that carbon of benzene. And so as you can imagine, that species is sort of a mouse fart away from being nitrogen gas, right? So this turns out to be a very good leaving group. Okay, and so that's something that we can exploit by reacting diazobenzene with nucleophiles. So I want to spend a brief amount of time talking about the mechanism for how we form the diazonium group from aniline. And then what we're going to do is look at a few reactions, and that's where we'll stop for today. And so what follows is probably the most complicated mechanism that you guys have seen in this class so far, but we're going to take our time and look at it. And you guys, if you have questions, you can always reach out to me and we'll talk about it. So this is going to be the mechanism we're going to trace out, wherein we convert aniline to the diazonium species. So to do this, we got to start all the way with the reagents on the line, sodium nitrite and HCl, to figure out how we can get that thing to be reactive. All right, so here is the Lewis structure of the NO2 anion. And when that material reacts with hydrochloric acid, we're going to start this whole process off with a series of acid-base reactions. So we'll protonate that NO2 negatively charged oxygen, and then we'll protonate it again with a little bit more hydrochloric acid. And what, of course, this does is give me a situation where I have now a good leaving group. Got this protonated, doubly protonated oxygen. And so that material can steal those electrons away from that nitrogen group, spit out water, and generate the first key intermediate in this process, which is an NO cation. This is known as a nitrosonium ion. Okay. That nitrosonium ion is actually what's going to end up reacting with aniline. So when that forms, aniline is going to come to the party. I'm just going to abbreviate it as pH for phenyl. Aniline's going to use its lone pair electrons to react at that nitrogen. So it's going to react with that positively charged nitrogen to form a new bond. All right, and so then I'll get this complex. And what will end up happening here is now I've got some water in the system typically, because we're using hydrochloric acid that's aqueous. That water can act as a base. It'll pluck off one of those hydrogens. And what ensues next is just a series of proton transfers where I've plucked off that hydrogen, so now I've generated H+. From, well, what I should really think about is the fact that I've generated hydronium, as I plucked off that hydrogen. And so now I can protonate that oxygen on the end. Now I'll get this material. And so now I can dance some electrons. I can fold in one of these lone pairs from that nitrogen closest to the benzene ring and pump those electrons onto oxygen. So now I've made one of the two double bonds of the diazonium. But what has happened now is I've made that nitrogen positive. If that happens, now water can act as my base again and pluck that hydrogen off to make a neutral species. Plus hydronium again. And so now I can have that water pick up that hydronium proton. We are almost home. We get this material where I've got a decent leaving group here on the end. Got an extra lone pair on that nitrogen close to the benzene ring. So if I pump those in to form that triple bond of nitrogen and spit out water, I will make the diazonium. Okay, so that's complicated. Let's talk through it one more time. Okay, so we're going to start up here. Start with the NO3 anion. It's going to pick up a proton from hydrochloric acid. Going to pick up another proton from hydrochloric acid. That's going to allow for this water to leave. It's going to make my nitrosonium ion. That's going to be the electrophile that reacts with aniline. The nitrogen will dump into that nitrogen positive charge. It's going to form this nitrogen-nitrogen bond, but it's also going to make the nitrogen on aniline positive. Water can come in and pull that hydrogen off. That's going to allow for an acid-base reaction between that oxygen on the system to pull off that hydronium. That species can then move electrons around by dumping electrons from the aniline nitrogen towards the other nitrogen and relieving one of those double bonds on oxygen. Next, water can deprotonate that newly formed positive charge on nitrogen. Gives us this neutral intermediate. That neutral intermediate will pick up a proton from hydronium. Finally sets us up with this system that can move electrons around to form the nitrogen-nitrogen triple bond and eject water, leading us to the diazonium product. All right, so that's complicated. Certainly not something that I'm going to spend a lot of time on as far as testing goes, but I do want you to spend enough time with it to recognize that it's all steps that you probably could figure out, right? It's all just acid-base chemistry and moving electrons around. All right, so the next question, however, is what can we do with diazobenzene? So here's some reactions of diazobenzene. All right, so what I can do with diazobenzene is I can take that material, which now has a very highly reactive into leaving group, and I can treat it with a series of reagents. So I can add to the halogens that I can install by using copper iodide. So remember, in our electrophilic aromatic substitutions, we could only add in chlorine and bromine. Well, I can add an iodine using copper iodide. I can take this same material now. Instead of using copper iodide, I can use copper cyanide, and I'll use that CN nucleophile to spit out the nitrogen gas and install a nitrile, so I can get benzonitrile. So these reagents that use copper, this is known as Sandmeyer chemistry. Okay, but it turns out we can do other things with the diazobenzene, since that's such a good leaving group. I can treat that with a material known as HbF4. HbF4 really is just a source of F-. So this allows me to access the other halogen in the group, where I can replace that diazo group with a fluorine. So now I have a way to get around and add on all of the halogens in the list. So I can use fluorine, and then the final couple that we can do is if I take that diazonium species, sorry, let me draw it a little bit better. So if I take the diazonium species and I cook it up with water and enough heat, you might imagine that I can just spit out that nitrogen leaving group with water and leave behind an OH. So this is one of the few ways that we've learned that we can make phenol. And then finally, I can do what's known as a proteolysis reaction. So if I take that diazobenzene material and treat it with H3PO2, so a specific acid, I can remove that nitro group and that diazo group and replace it with a hydrogen. So why the hell would you want to do that? That's a reasonable question. What more relevantly people will do is use the heavy isotope of hydrogen deuterium. So I could use DPO2, and that would give me a nice route to a monodeutyrated benzene ring. So I could actually install the deuterium atom. Okay, so I know that was a lot of new reactions, but again, don't worry about this for your current upcoming test. We will build on these reactions after your test on next Monday. All right, I will see you guys in class on Friday with your exam. In the meantime, if you have questions, don't hesitate to reach out.